All right.
No introduction needed. So
Okay, great. All right, so thanks guys for inviting me to give this talk in the group. It's about how to best teach Prolog. You know, there's a lot of really good material for Prolog already out there. So I'm not trying to like give a list of topics or say what materials we should use or anything like that. Basically, it's just to give some lessons or thoughts from our experience teaching Prolog. This is mostly from our experiences to CS undergrads at UT Austin first, then at University of New Mexico and Technical University of Madrid. And also some experience from the point of view of systems, you know, as developers of the Shell Prolog system, where we added some stuff, you know, to help with teaching, to help us with teaching, and other people that use it. Now, the CS undergraduates have typically been exposed to other languages like imperative, object-oriented, and sometimes functional, and sometimes to logic, specifications, and some numbers of program implementation. This has two implications. One is it's a challenge to make the material attractive and intriguing and challenging for them, for this audience, because they've already seen a lot, no? But on the other hand, they're also a great audience because they can appreciate and be impressed, you know, when they see that this is really different, no? Anyway, and I put a pointer there to some place where to find some material. First point that we'd like to make is that Prolog and logic programming in general and constrained logic programming should be taught in CS programs. It's one out of a very few set of programming paradigms that we have, but it's also really interesting and it's different and it's very useful. So I think we can argue, you know, preaching to the converted here, but that a CS graduate is simply not complete without the knowledge of Prolog. And of course, we should also ask ourselves if we how to teach it in other majors and also in schools and so on, and the group is obviously concerned with that. Now, Prolog has to be taught, but it has to be taught right. This is the main thing, because otherwise it's counterproductive. It's a different paradigm, and because of that, it needs to be taught differently. And in the way in which many times Prolog is taught, which is within a programming paradigms course, you know, where basically you get a couple of weeks of Prolog, can sometimes actually be counterproductive. It's really hard to teach what Prolog is in just a couple of weeks, and especially if it's emulated in another language like a scheme and so on. This really does not do the job. So this, of course, raises a question that I'm not going to address here, but it's a very interesting question, is what do we do if that's the only slot that we have available for teaching Prolog in college? So that's a challenge that we put on the table for the LP community and for the group. I think this is something that needs to be addressed. Now, what's the main message? The main message is that show the beauty of Prolog, because it's there. I mean, obviously, we know, no? And the first thing we do, we start by explaining Green's dream, to explain the motivation. And we start with the question of what is the best way to program a computer. And of course, you can use programming languages, you can different programming languages, different approaches, and so on. But there's a different way, and the different way is exemplified by Green's dream. What we call Green's dream is that if you have a deduction system, if you can program in the computer a deduction system, something that can prove theorems, then if you have a problem and you want to solve it, you can basically just write the specification, the representation in logic of what your problem is, and then if you can ask questions on the deduction system, if the questions follow, if the questions that can be answered that follow from the specification, you should be able to get correct answers, correct results, in a way without correctness proofs, without programming, in quotes. The question is if this is possible, and this is the question that we pose to students, no? And we say that Prolog is the materialization of this dream, of the first, and Prolog and its successors and evolution is the materialization of this dream. And basically, the deduction procedure is SL resolution over form clauses, and this is what we want to show. Now, to show how this works, use a program, a simple program. We start with something like, for example, calculating the squares of the naturals that are less than 5. we can show the imperative program with a loop and so on in whatever imperative language. And the question is it correct? And of course, to show that the program is correct, the first thing that we have to do is to say, what do we mean by the naturals, the naturals, the squares of the naturals that are less to 5? So we have to write a specification that has to be done in logic. So we go ahead and we try to develop the specification, which will turn out to be a program. So we do it, by the way, with breadth first search. I'll talk about more about that later. But we define naturals. I'll go fast because we know about this. No? So we define naturals, we define less, all in piano. Addition, multiplication, the squares as multiplying a natural by itself, and then we define the actual what we actually wanted to do, which was to output the squares of the naturals that are less than 5. And then we show, sorry about that, and then we show that if we ask the system to generate the output, it does. And the cool thing, I mean, so we generate the result from the specification. And the cool thing is that we can generate many more things that we intended from this specification. For example, we can do square roots. Of course, many questions raised immediately, and termination and so on, and those have to be tackled, and we will tackle. So we can use other examples. This one is great. For example, this circuit topology where you describe what an inverter is, what a NAND gate, some resistors, and then you can ask if there's a NAND gate in this circuit, and the system just finds it and tells you where the NAND gate is. Anyway, now this is the part of showing the beauty. Now we also have to show the limits, basically expectation management, right? So we enter in a discussion of the logic, so different logics that we have, for which ones we have effective deduction procedures. Then we justify, you look at propositional logic, at higher order logics, and so on. This is all at a conceptual level, because some of these students may have seen logic before, some not. It doesn't matter. What you wanted is to get the concepts. So we justify the choice of first order logic and SLD resolution because of the semi-decidability, which we explain with pictures. I'll show that. So this gives rise to the choice of classical LP logic programming in the Kowalski-Kommenauer sense. Another thing that is important is to show that the logic programs are both the logical theories, can be logical theories with declarative meaning, and procedural programs that can be debugged, followed step by step, etc. This is something that we find that is important, this duality. And to show that how you can go from executable specifications to efficient algorithms, and that this can be done gradually as needed. Okay, so this is an example. There are many more, but an example of the definition of remainder, where we define that z is the remainder of dividing x by y. We put the definition. No, z is that remainder if there exists a q such that x is equals to y times that q plus z, and that z is less than y, i.e. the remainder is less than the original number. Okay, now we can write that directly. The fun thing is that we can write that directly in Prolog, in pure Prolog, and it runs even backwards. You can say, okay, give me two names, so that's the result, the remainder is of their division is 1, and it gives us pairs of numbers of division is 1. At the same time, of course, we can reason about how this works operationally, and there's the enumeration and backtracking and so on, or we can write a more efficient Prolog version, at least efficient for one mode, which basically is a loop, that is doing subtraction, that is running add backwards and doing subtraction, therefore subtracting the number until there's only the remainder left, which works exactly the same, and but allows us more to discuss about modes and how they affect determinacy, cost, termination, and so on. Another thing that we think is important, again, this is not in order or anything, it's again, ideas and thoughts of things that we believe are important to convey. Another thing that we think is very important is to show how unification is a device for constructing and matching complex data structures with declarative pointers. This idea of declarative pointers, of variables as declarative pointers, that we think is important. And we can do that really just playing with data structures in the top level and giving the data structure class, building structures and building lists and linked lists and so on, like and trees and so on in the data structure class. So doing something like this. I create some data structure and I point X to it, and then this has a pointer here, K, and here it points to G of K, and this K and this K are the same. So, and this is a free pointer that I can fill later, and then Y equals A basically means that Y now points to A and Z and so on. So we show the heap memory at different points. This will be at this point, and basically when we make this call, basically what we're passing is a number of pointers to these data structures built in the heap. So this duality between terms in logic, looking at it with the glasses of logic and the glasses of data structures and programming language is fundamental for us. Another thing that we think is very useful is to use types and properties in general and define them, of course, defining them as predicates, and those show how you can use them to check if something is of the type, dynamic checking, or to run it backwards to generate the inhabitants of the type. And then you can get property-based testing for free. For example, if you define NatList, that can be used to check if something is a list of naturals, or to generate lists of naturals. And then you can play with the control rules and maybe do random generation or breadth first generation to be fair in the enumeration and things like that. That's a lot of fun, and they enjoy it. Another thing that is super interesting to show, of course, is the 3-line meta interpreter and an adorned one that counts steps or does prints the calls and the successes or whatever extra thing on the fly. First, because it's a thing of beauty, or it's probably the only language in which you can write something as complex like that in 3-line, and an excellent demonstrator of the unique powers of Prolog. Of course, it's important to use motivational examples that involve search, like puzzles and so on, because search is a unique characteristic of the language. And of course, it's important to give advice on how to control it. The use of ordering of clauses, ordering of literals, the use of cuts and other control structures. All right. Things that are also important to show that are greatly appreciated, of course, are incomplete data structures, different lists, different trees, different data structures in general. Emphasize the complexity advantages, DCGs, of course, and parsing. And also show that there are plenty of interfaces to other languages, to data representations, and so on. So these are a few topics that I think should not be missed. Another important thing is to dispel myths and misconceptions. People may come with or may have heard things about Prolog that are misconceptions, and which are really not, or may have been in very early versions of Prolog, but are not anymore. A very important thing is to explain termination. The misconception is Prolog doesn't terminate loops. It's hard to find sometimes gets in a loop. Well, the first thing is that, of course, non-termination is a fact of life of any powerful programming language, any Turing-complete programming language or powerful proof system. But the fact that it's a fact of life, it's likely still to discourage beginners if it's not explained well. No? So we have found it, very useful to, as I mentioned before, to use or build a system. Is really easy with a meta interpreter or whichever way you want, to run alternatively and selectively in breadth first, iterative deepening, tabling, etc. Because all these have different characteristics and a lot can be learned. No, the basic thing we believe is to start with breadth first. The first examples and so on, to run them in breadth first, because everything works in breadth first. No, and then explain the shape of the tree, and that the solutions are at finite depth, that there are possibly infinite failures, etc., and how breadth first works and so on. So the tree that we use to explain it is, we make it clear that the solutions are all at finite depth. There's a finite number of steps to the solutions. Then there are failures that are a finite number of steps, and there are failures that are at an infinite depth, and you cannot know that they're failures. So that, you cannot reach them. And then, of course, once they have this picture in their mind, and also that this embodies termination, what you cannot avoid, the problem of non-termination, which you cannot avoid. Then explain that with depth-first search, you can find solutions, but you may leave solutions. You may fall down an infinite tree. But if you go breadth first, you will always find the solutions, all the solutions, before you fall down an infinite tree. I know everybody here knows that, but just that it's this tree picture it makes it easy for them to understand why their programs sometimes don't terminate and what they can do about it. No, for example, do that first, that you switch around the infinite failures if you can, and so on, and why breadth first does work, and iterative deepening and all the other methods. Anyway, so like I said, it's important to relate this semi-decidability to the halting problem, that nobody, Prolog Logic, no other two incomplete language can solve that. Tabling helps, of course, for example, so this is a good time to introduce tabling, which is important, of course, and to discuss the advantages and disadvantages of the different search rules in time, in memory, and also to motivate the choices done in Prolog, the choices that are there by default, because they do make a lot of sense, if you take all these things into account. No? More things along these lines, showing that Prolog arithmetic can also be reversible. A lot of people may have heard, or if you only teach is, obviously, you get disappointed, no, because nothing runs backwards and so on as soon as you start using arithmetic. So a good thing is for us, it's a very good idea to start with piano, because it's beautiful even if slow. Then we can justify the Prolog, the classic Prolog arithmetic for efficient, and then of course show constraints and show that things are beautiful again and also efficient. So that is great. The occur check. So show that the occur check is available if needed. Why there's a built-in for it instead of being by default. You can have a package that an expansion, a syntactic expansion that always calls or a flag in the system that always calls unification with occur check if you want. But in fact, in practice, it's not a big deal, no? And also, for example, the existence of infinite tree unification as a constraint domain, which sort of solves this in a different way. Regular trees and so on. Show that Prolog can be pure. So there's this conception that Prolog is impure. No, only a few of the Prolog built-ins are impure. Prolog by itself is not impure. It's pure, and it can be pure despite cut and assert. A good idea, for example, that we do is to have a pure mode in which, in the implementation, have this pure mode in the implementation that only any impure builds are simply not present. You cannot call them, and that's helps a lot sometimes. And also, of course, to develop pure libraries. It's important to develop pure libraries and to develop pure built-ins that can be loaded alternatively to the default, or let's say ISO built-in. But also we have to accept and show the students that we have to accept impurity sometimes. But in those cases, the idea is to keep it as encapsulated as possible. Negation, of course, is complicated. Of course, we explain negation as failure. It's important to devote time to discussing the limitations and maybe teach them to check that they some simple check, like for example that the goal is ground before calling negation and so on. That this could be very useful. But also some other types of negations can be explained, and things like SCASP or ASP and so on. Convey the idea that Prolog has many applications and uses, demonstrating it, showing many examples of impressive applications that we have. For example, the Prolog yearbook, there's quite a number of them, and there's many others, of course. A thing that we believe is important is to convey the idea that Prolog is in many ways as other languages. It's not strange. It's just that it adds more. It adds unique and useful features. So in a way, Prolog subsumes, it does, so show it that it subsumes functional imperative programming, imperative after SSA, if you want to think about it that way, but it adds more. It's basically a standard language. It works just like any other language if you use it forwards, if you use it in one direction, and there is only one definition per procedure. So if you do that, then it's a standard language, more or less, with very sophisticated pattern matching, let's say. But it can also have several definitions. I mean, you cannot do that in other languages. You can have several definitions for the same procedure. So this is in addition to, and this allows you to search, to run backwards and so on. But this is in addition. And the way that is implemented is in a fairly standard way. If they have some notions of programming language implementation, everybody understands forward continuations, the stack, that when you call something and return, you have to save the return address in a stack. So you have forward continuations. So think of backtracking as backwards continuations. You have another stack where you remember where you can go to if you fail. So it's the same technology as going forwards for going backwards, for backtracking. So that makes them, that they don't feel like there's something weird going on. It's actually something very, very standard in programming language implementation and very efficient. It's important, I mentioned before, to show that it can have types, that you can do types. You can do also modes and assertions if needed. And of course, it's also important to show that Prolog can be fast and it can be compiled. It can generate standard executables. These are things that are important for perceiving the practicality. That it's not just some toy that you write something on the top level and so on. No, you can put a main and generate an executable. So this, I think, it has to be shown. It has to be shown every time. And then, of course, that it has environments and tests and auto documenters and linters and great environments in general nowadays. It used to be, this is it was not the case before, but it is really right now. And then my final slide here is some discussions of system types that we use for teaching Prolog. Of course, there's the classic installation. You download your Prolog system, you compile it, you install it, and you run it in the top level and maybe inside Emacs or VSC or whatever your environment is. This is the most appropriate, in our opinion, for advanced students because it shows real use. It shows that it's a serious competitive language with a compiler that generates executables, same thing as before, then that you can develop in your standard development environment, like when you're doing C or Python. But of course, nowadays, fortunately, we also have playgrounds and notebooks. I mean, we have some descriptions of this in the Prolog paper. So the Chow playground active logic document, Swish, of course, from SWI, Tau Prolog, Sixtus plus Jupyter notebooks, also very nice. So we have very nice environments that are much easier to use and they're great. This can be attractive for beginners, for younger students than in college. Also, because many places may not have personnel to help with machines, with installation, with so on. So for this, you only need a tablet. You can just connect to the internet, and that's really, really great. No? There's the issue of whether they're server-based or browser-based, whether they're running in a server or they're running in your browser. And of course, it's very useful that also for having in manuals and so on, executable examples, in tutorials and so on, that you can run the examples in the tutorial. So these are great things to use. Anyway, so what we do is offer both types, and students use one or the other depending on their abilities, which we try to force them to install because it, like I say, it gives an impression of a serious language. But if some have difficulties with those things, then that's okay. You could do block-based versions that are very useful for the youngest. Lara Checky's paper in the Prolog book talks about that. There's a nice good tool for kids developed by Jose Francisco Morales Salvador for the Prolog year. See that also. The one thing is that the system should allow covering the things that you want to cover. So, but I think most systems do it now, most Prolog systems, right? To have pure LP. I mean, if the system doesn't do it, it's easy to do with just a meta interpreter. ISO Prolog, of course, you have to have support for ISO Prolog. Higher order support. You may want to have functional syntax or not really necessary. Constraints. Very good to have constraints because of what I said, to show that the arithmetic is reversible and so on. Tabling, I didn't mention before, but that's important also, I think. And it's useful if you have ASP or SCASP in the system. And let's go back for a second. Yes, I thought I was forgotten something, but I did not. Anyway, and I finish here. I'm right on time, I think. There's much more in the Prolog book, so I invite you to look at the paper there. But anyway, this was just a few thoughts, on what we think is important, what should be emphasized when you